My project is working with Dr. Justin Wilson is modeling quantum dynamics with bond percolation. This figure, the left side of this figure is a quantum circuit where X represents position and T represents time as you go up the circuit. To the right, this lattice represents, each bond in this lattice represents the entanglement, these lines on the quantum circuit. You see where these aren't connected, it'll be a dotted line. When they are connected, it'll be a filled in line. Whenever you measure a quantum circuit, measured entanglement is broken. And you could represent that in the lattice by removing this bond and replacing it with a dotted bond. That's how you can see this lattice to the right is starting to correspond to this quantum circuit. The reason we would want to do something like that is quantum simulations are very slow. So, when we measure this quantum circuit, we can do something called a minimal cut between positions. So if the qubits live atop this lattice, and you measure how this side of the lattice is connected to this side of the lattice, that's the same as measuring something called the Hartley entanglement entropy. It will equal to the Hartley entanglement entropy of the quantum circuit. As I said before, quantum simulations are slow. Using a percolation model like the tilted square lattice, we can perform a measurement. We can find the quantum entanglement entropy of quantum circuits up to sizes of 100 qubits long or even up to 1,000 qubits long. But when we use pure quantum simulations, the size, the qubit length of the circuits, we're pretty limited in how long those are. Like this revolutionary Sycamore chip with Google, it's 53 qubits long, but and it was very recently created, and it's groundbreaking. But we can do 53 qubits pretty easily using a percolation model. In our project, to make our percolation model, we created a program that runs three algorithms. The first algorithm, a columnar disorder algorithm, basically each little zigzag represents a different qubit. Like the qubits are up here over time, and before we perform any measurements on the quantum circuit and the lattice correspondingly, when we cut the bonds, there's already going to be qubits that aren't connected. There's already going to be measured little entanglements, like you see the dotted lines. But with columnar disorder, each color, each zigzag, each qubit has a different probability of having a broken bond, like a measured entanglement, no entanglement. So this qubit right here, it might have a 1/5 chance of having a measured bond already, but this one might have a 1/3 chance. So the program creates a lattice with columnar disorder. It has a different probability in each qubit, and then it performs something called a wedding algorithm. So the wedding algorithm, you call it that. You can kind of envision it as maybe pouring water over. This represents the lattice. Pouring water over it and seeing if the water how many cuts you have to make for the water to flow to the bottom. That's a way of visualizing it, but really it's by finding out how many cuts, in this case 4, are needed to separate this side from this side. That's something called the minimal cut or the half cut, because there's two halves. And that, in that case, as I mentioned earlier, is equal to a corresponding quantum circuit. It's something called the Hartley entanglement entropy. The final algorithm is something called the long cylinder algorithm. It's called the long cylinder algorithm basically because in the case of our lattice, the left edge and the right edge are connected to each other, so you can kind of envision it as a lattice, like the lattice making a cylinder, like a netted cylinder. And in the long cylinder algorithm, we started with the final time slice. We go through, we perform the wetting algorithm and columnar percolation algorithm, or columnar disorder algorithm, and then after finding the half cut for that, we build up another time slice, and we run the same program again. Basically, we're building a cylinder as we go, which is the lattice. And in this case, the reason we do the long cylinder algorithm is so we can, to very late times, which is a tall cylinder, we're able to perform this wetting algorithm and columnar disorder algorithms. At this moment, we have not gotten all the data yet, but what's expected to occur is this is a graph of the Hartley entanglement entropy, like it's the Hartley entanglement entropy growth for systems of sizes 16, 24, 32, and 40, and this is how they grow over time. Notice there's two different colored lines, the red lines and the blue lines. The red lines represent we're performing this simulation on a circuit or a lattice with a product state, which is basically, it starts out with no entanglement at all. So you see it starts out here at the bottom and it begins to grow. The entangled state is a lot of entanglement, basically the opposite of the product state. It starts up here, but then it shrinks. And you'll see, you'll notice that if they, for circuits or lattices of the same size, like you'll see the faded lines, they both, over time, as time goes to infinity, they both start to equal. Their entanglement growth, their Hartley entanglement entropy start to become equal. It's the same for L equals 40. You'll see the darkest line, and then the 32. They all start to equal each other over time. Another thing you might notice is the x-axis down here is log of t. You notice at a very small t, it kind of looks like a straight line going up. This is because at small times, the half cut, which is L over 2, or the entanglement entropy, looks like the log of t, like a graph. Like if this were just t at small t, like instead of log of t, this were t, it would look like the log of t. But at larger times, you'll see it starts to curve, and if this were just t, then this would look like a graph of the square root of L, actually. So small times, the Hartley entanglement entropy grows like log of t, and at larger times, the Hartley entanglement entropy grows like the square root of L. And you remember that L is the length of the amount of qubits, and the time is just that's over time. Our goals for this project, it's not finished yet. We want to obtain large data sets for different parameters, like different times, different lengths, and plot our data. And also, we want to calculate, right now we're calculating the half cut for the entanglement entropy, which is, as I said before, just how this side is connected to this side, which is, when I'm talking about the circuit, it's saying how is this, how are these qubits entangled with these qubits? And that's called the half cut on when we're talking about the lattice. But we might want to try something called tripartite mutual information, which is basically different. Instead of a half cut, we might just say, instead of 2 equal halves, it's just 2 sections. Like maybe we just do, how is this single chunk connected to this chunk over here? Like how is this qubit connected to all the other remaining qubits? Anyways, that's our project. Does anyone have any questions?
I have 2 questions. The first is that expected results? Are those real results, results generated from like an equation, or someone else's results? What does that mean?
Dr. Wilson, he recently published a paper that used a percolation simulation, which is what our project is based off of, and this is the results from his.
Okay. Other question. Oh,
sorry, what was your other question?
Other question. It said that quantum simulations were slow, but then you said you could easily, with your percolation model, I guess model more qubits than like a advanced quantum computer. So does that mean you can like simulate more, but it's slower, or is your percolation model not a simulation, or what does that mean?
Sorry, when I say quantum simulations, I mean not the percolation simulation. Quantum simulations, they run on the circuit. They don't create like a lattice, percolation lattice like we are. Our percolation lattice is able to run quickly, and it's able to work for very large qubits. The actual quantum simulations they're much slower. Like when you're working with qubits, like the times it will take are huge. And with the percolation, like I can run on a little crappy computer, like I can run something with 53 qubits, like this groundbreaking Sycamore chip. I can run that in like a day or less.
So is the Sycamore chip a classical computer emulating a quantum computer?
Sorry, this is fully quantum. This runs quantum simulations. This doesn't use the percolation simulation that we're using. This is that's why this is limited to like 53 qubits long. That's pretty impressive. But we're able to do that with the percolation model because we're not doing quantum simulations. We're able to do 53 qubits much easier.
Wait, why is it called a simulation if it's...
Sorry, well, there's the quantum simulations and then there's the percolation simulation, which is also, I guess quantum simulations is the best way to put it because they're all quantum simulations because they're simulating something that's going to tell us something about a quantum circuit. But when I say quantum simulations, this is not related to the percolation simulation that I'm using. The percolation simulation is representing a quantum circuit. But when I say they're using quantum simulations, it's not using this percolation lattice at all, which is what is helping us do it to these extremely large qubit sizes. Like this is what helps us do it quickly. But they're not using that. They don't use that because they just do simulations on this circuit. We are doing it on a lattice that represents the circuit, and being able to work on the lattice makes our program able to run much faster.
Okay. Wait, so are quantum simulations separate from the Sycamore chip? Is that like another method to emulate?
The Sycamore chip uses quantum simulations.
But it's a quantum computer?
Yes.
Okay. I guess I just don't know what that is.
Sorry, I don't think
good.
I answer you correct.
I might clarify a little bit. So the Sycamore chip is a quantum computer that does like fully quantum, like I guess simulations. But like you can also simulate qubits on a classical computer. There you can only get to maybe 24 qubits or something. So like on your laptop.
More questions?
So, understand the quantum simulations, the algorithm that you're setting up here would essentially topple that of the chip?
These are There are a lot, the percolation, we can do, are you asking if it's faster than the chip? You're saying?
Exactly. Essentially, would it be like better, and we're working towards like maybe like a sort of replacement in a sense?
I'm
Or
not.
is a convenient alternative to doing the same problem?
I guess, I think, I suppose so. I'm not, I'm sorry, Dr. Wilson knows more about this than I do, about the Sycamore chip and
Okay.
percolation in like actual applications. I'm sorry, I'll have to get back to you on that later.
It's okay.
Any more questions? Or?
Okay, there is no more question, just Levy.